Hi everyone, welcome back. Now today we're going to move off onto chapter 10. And in chapter 10 we start talking about correlation and regression. Alright, now regression, we're going to be looking at what is known as a linear regression. Alright, so once we get to that topic, we'll go ahead and we'll explain a little bit more as to what that is and how it ties into our lesson. For the first part, we want to focus on correlation, and that's where section 10.1 begins. We want to look at the correlation between these two objects. Alright, so what we're going to do is we're going to start by defining correlation at the beginning. And correlation just measures how strong a statistical relationship is between two numeric values. Alright, so again, kind of like before where we were doing this confidence interval or this hypothesis testing on two different variables, now we want to see how strong is that relationship between those two variables. In order for us to proceed, we then need to explain what is our explanatory variable and what is the response variable. So the explanatory variable, this one here is going to be a predictor variable. Predictor variable versus a response variable. A response variable is basically the outcome. Now, as you might have seen in an algebra class, when we start with linear equations in an algebra class, typically we say, hey, we have this independent variable and then we have this dependent variable that we look at. In other words, your x and your y variable. In this particular case, in statistics, we do the very same thing, right? The only thing is that we're going to label them slightly different because, again, at times we don't look at these responses in terms of a quantitative form. Sometimes we can look at them in a qualitative form. So what we're going to start here with is this explanatory variable is going to be the independent variable used to predict, there we go, used to predict or explain differences in a response variable. Alright, so again, in here what we want to focus on is that we have this independent variable, and this independent variable is just going to be used to make these predictions, or we wanted to explain the differences in what we're going to call this response variable. Alright, so again, there's two parts to this. One is the independent variable and the other one's going to be the dependent variable. So now, what is this response or this outcome variable? Alright, so let's go ahead and let's start defining that. Here, we're going to say that this is the dependent variable found as an outcome, that is measured following a manipulation of the explanatory variable. There we are. Alright, so now when we want to determine which one of these statements are we using when we're looking at, or when we're trying to identify which is the independent and which is the dependent variable, what we typically ask ourselves is which statement makes more sense, right? So to illustrate this, what we're going to do is we're going to work on this example really quickly. And this example says that a researcher wants to examine whether babies fed on breast milk are more or less likely to be ill. So statement A says that feeding a baby on breast milk causes resistance to disease. Or B, resistance to disease causes a baby to feed on breast milk. All right, so we need to identify which one of these statements makes more sense based off of the example that we were just given, right? So do we want to say that feeding a baby on breast milk causes resistance to disease? Well, yeah, that's kind of like this right here is kind of looking at my explanatory and then looking at the response variable, which will then cause some resistance. All right, whether part B, we're saying, hey, resistance to a disease, so this is kind of putting that response variable first. Resistance to a disease causes a baby to feed on breast milk, right? So it kind of gives us the response and then the explanatory variable second, which this statement kind of doesn't make sense, right? So for us, or for our answer that we're looking at, we want to look at statement A. Statement A makes the most sense logically, and it has this explanatory variable and this response variable. Now, can we identify which is which? Well, the presence or the absence of milk. This is your explanatory variable. That's the explanatory variable saying, hey, there is something here, right? Now, what is happening to that? Well, if there is presence or if there is absence of milk, well then there might be some resistance or lack thereof to some sort of disease. And this here is the outcome, right? Or in other words, the response. So this in here is the response variable that we want to observe. All right, so again, very different from when we work in algebra, when we look at our x as an input, our y as an output. In here, we start classifying explanatory versus response, and then we start observing how are those relationships working with one another. All right, so on this next example, we then want to see, or we want to identify the explanatory and response variables in the following examples. In part A, we want to look at an experiment. We want to look at the experiment was conducted to test effects of sleep deprivation on humans' response times. Okay, so here we need to look at the independent variable. What are we going to use to predict or explain these differences? Right? So what we're doing here is we're looking at this first part that we want to look at the effects of sleep deprivation. All right, that's going to be the first part. So this in here is your explanatory variable. And I hope you all are okay with me abbreviating these. I'm going to abbreviate explanatory variable as EV and then response variable as RV. All right, so we got the effects of sleep deprivation. That was our explanatory variable. Now the response variable. Well, the response variable is just basically measuring the human response times. That is the response variable. Now, I want you to try part B. All right, I am going to go through part B very similar to how I did part A, but in a sense, I want you to put pause on the video and then try it yourself. See if you can identify what is the explanatory variable, what is the response variable. All right, so if you want to do that, take some time now, put pause on the video, and then we'll carry on in just a bit. So the researcher Penny Gordon Larson and her associate wanted to determine whether young couples who marry or cohabitate are more likely to gain weight than those who stay single. So again, we want to look at what is this independent variable? What are we trying to observe? All right, and the thing that we're trying to observe is we're trying to observe young couples who marry or cohabitate. All right, so this is all your explanatory variable. That's the continuation of it. That's all the continuation of the explanatory variable. Now, what is it that we are measuring? What is it that we're looking at? Well, now we're looking at, are they likely to gain weight than those who stay single? This is the response variable that we're looking at. All right, we want to see, do they gain more weight? Do they gain less weight? All right, how does that compare to couples who are single? All right, perfect. So now that we got this warm fuzzy feeling for explanatory and response variables, we now want to kind of put a pin in that really quickly, and we want to move over into scatter plots. Now, if you were following along from the very beginning of the semester, we talked about Section 2.4 while we were still face-to-face in class back in March, I believe, where I said, hey, we're not going to cover Section 2.4 just yet because we're actually going to wait for Chapter 10. All right, so when we start on scatter plots, if you go back to Section 2.4, that's actually what we look at there. So when we start this section on scatter plots here, this is that section back in section 2.4 where we would have started looking at scatter plots. So if you want to take some time and if you want to go back to section 2.4 and look at it, be my guest. That would definitely help you all cement what we're going to be working with in this section. Now, a scatter plot is basically a plot of x and y values that contains quantitative data. All right, now the way we use scatter plots are very beneficial for us to try to help us understand if there is a relationship between one variable and another. Now, what type of correlation or what type of relationship do we look at? Well, that relationship is going to be called a correlation. So we could either have a positive correlation, a negative correlation, or approximately no correlation. So to start off, a positive correlation. How do we know if we have a positive correlation? Well, variables, and this is both variables, the x variable and the y variable. Variables move in the same direction. In other words, as your x's increase, so do your y's, right? And that goes along with these points here. As x gets larger, y gets larger as well, as we start looking at this graph. Negative correlation. In a negative correlation, variables move in opposite directions. Now, what does that mean? Well, as x increases, these y values are going to decrease. So the y values are decreasing, but the x values are increasing. All right, so if I want to find a pair here, my x value went large, but my y value went down. If I find one here, then that means my x value was small, but my y value was large. As x gets larger, y values get smaller. And again, these could be also flipped. It could be that as your x values get smaller, your y values get larger, and you look at a slightly different correlation. All right, next one. Approximately no correlation. All right, so if we're looking at approximately no correlation, this is going to say that there is no apparent relationship between the two variables. In other words, it does not satisfy positive and it does not satisfy for a negative correlation. All we say is that there is approximately no correlation for the data that we are observing. That's it. All right, so now that we have more definitions for correlation, let's start looking at how we're going to start developing this whole process for a linear relationship. All right, so to test for a linear correlation, we attempt to draw a line that best fits the data. Every linear correlation is expressed as two features. All right, we want to know the strength and we want to know the direction. All right, so we're going to be looking at strength and direction. So for the part where we say that we want to look at strength, what we really want to look at here, or what it is that we're looking at, is how close the points fall near a line. All right. Now, again, we want to see how far are all of those points near a line. So if you look at the positive and the negative correlation on this first page, look at all of these points that are near those lines. All of the points are fairly close to this line that we have drawn here. Therefore, that strength is pretty good, meaning it has a strong strength. All right. Now, typically, what we're going to do is we're going to start measuring this with a numeric value. Measured with a numeric value. And the thing behind that is that we don't want to just look at a data set and say, oh yeah, automatically just because I see it, it means that this is going to have some strong correlation. No, we want to make sure that we're able to back up our arguments using math. So when we back up our arguments using math, we typically try to look for this numerical value that shows us the strength of this correlation. All right, so next we want to look at direction. So we want to see what is the direction for this correlation if there does exist a correlation. So we want to look at, as the x values increase, y also increases. This is going to give us a positive correlation. Or, that was one option. The other option, we can have that as x decreases, y decreases as well. All right. So, again, this is going to show that we're going to have this negative correlation. Correlation. So again, we want to look at those two values, right? Do we have a positive correlation or do we have a negative correlation? One or the other. All right. Now, the strength of the linear correlation, so back to this numerical value that we were looking at. The strength of the linear correlation is represented by a numerical value called the correlation coefficient, otherwise denoted by the value of R. So we're going to be identifying this correlation coefficient, and that in turn is going to tell us how strong this linear correlation is. So let's look at a few properties for this linear correlation. So one of the first properties is that the value of R is always going to be between 0 and 1 at all times. All right, so my correlation coefficient, the one that we find, will always be between -1 and 1. Awesome. Number two, the value of R does not change if all values of either variable are converted to a different scale. All right, that one's going to be very important there. If we use to convert to a different scale, then the value of that correlation coefficient should not change. All right, now let me give you an example for that. All right, say that we were looking at temperatures. All right, say we were looking at temperatures for a 7-day period, and we were measuring the temperatures, what we know here in the United States as degrees Fahrenheit. Well, if a researcher was doing the same observation, but let's say they were in Germany, they would be using a temperature known as degrees Celsius. Now, when both of the researchers, us here in the US and those over in Germany, published their studies and we look at the correlation coefficient, the correlation coefficient should be exactly the same for those two observations. Even though one scale is in degree Fahrenheit and the other scale is in degree Celsius, the correlation coefficient should be the same, simply because we're looking at the exact same values except with a different scale, meaning that the relationship should still hold. All right, now that's a very interesting observation. Number 3, R measures the strength of a linear relationship only. It does not measure non-linear relationships. All right, this is an important part here. Non-linear relationships, it will not measure it. So what do non-linear relationships look like? Well, they're going to look something like a logarithm or a parabola or some type of polynomial that we typically would look at in an algebra course. In this particular case, we're only going to be looking at a linear correlation. In other words, equations of lines. All right, so how do we then know which is a strong correlation and which is a weak correlation when all we know is that our R values need to be bounded between -1 and 1? Well, that's what we're going to get into next. And for that piece of information, we now need more of that scale, right? We need a scale to determine, well, what is strong and what is weak. Now, if you remember, back when we started in chapter 2, somewhere around chapter 1, chapter 2, and chapter 3, 4, 5, 6, we've kind of carried it over, was this range rule of thumb. All right, we were using this range rule of thumb to determine kind of when we have these unusual values or these significant values, right? Typically what falls outside of the 2 standard deviation range. Well, we're going to do the exact same thing here. We're going to identify that our center is going to be 0. Now, every time that the center is 0, our variation is always going to be between -1 and 1. The closer we are to -1 and 1, the stronger the correlation will be. In other words, that means we're going to extend past that 2 standard deviation point. And in turn, we then need to figure out what are then those critical values or those regions that we then need to test. All right, so we're kind of now going back into that hypothesis testing again, or that confidence interval building again, but this time around we're doing it with lines and what we call these correlation coefficients. So now that we got this a little bit more, let's look at this very, very important note. The note says that correlation does not imply causation. Just because we found a relationship doesn't mean that we found a cause. This is very, very important for us to know. That this just lets us know that there is some association between the variables. All right? So we must make sure we keep that in mind. Given that there's a correlation, it does not imply causation. One variable does not imply the other. Doesn't mean that there is a cause for that outcome. All right, so very important for us to make that distinction here. Now, what we're going to do is we're going to be looking at these scatter plots here, these 6 scatter plots. Looking at these 6 scatter plots, what we want to do is we want to choose a word from each category to describe each of these plots. All right, I'm going to do a few of them with you. That way we can start looking at them and we could then bring up a discussion if you want on the discussion board. So for the first one, top left corner, here we go. Does this scatter plot appear to have some type of correlation? Right? It does appear to have some type of correlation. All right. So in here I'm going to say this has a fairly strong correlation. So that has a strong correlation. All right, nice. Now, does that appear to be a linear, nonlinear, or no relationship? And the way we kind of view that is, if there's a linear relationship, then that means that we could probably draw a line that's going to be the best fit line amongst all of these points. Notice if I drew this line, all of these points are not too far away from that line. Therefore, again, that kind of represents a strong relationship. So this one, we're going to say linear. All right, does have a linear relationship. Perfect, it's strong. Now, what type of association do we have? Is it a positive, negative, or no correlation? Well, in this particular case, as x increases, y increases as well. So I have my x here and I have my y's here. So as x increases, y increases, which means we have a positive association. All right, looking pretty good. Now the correlation coefficient, the very last one here. What type of correlation would we see here, numerically speaking? All right, well, if it's positive, then that means this correlation coefficient is not going to be negative. So that automatically cuts out these first three in that first column. Secondly, the R value, or the correlation coefficient, closer to 1 is going to be the stronger correlation. So looking at these two values, 0.634 and 0.886, I would naturally choose 0.886, specifically because this appears to have a strong correlation, meaning this R value is closer to 1. All right, perfect. Let's look at the next one. All right, let's start off from the very beginning. Do we have a linear, nonlinear, or no relationship? Well, let's go back to my ruler topic here. All right, can I possibly draw a line that will best contain all of these points? Sure, there it is. All right, now naturally these points down here tend to fall further away, but that's okay. It's still a linear relationship. Next, is it perfect, strong, moderate, or weak? I would say in this case it's pretty moderate. All right, we have a moderate relationship there. Okay, not too bad. So is this positive or negative? So positive or negative? Well, as your x values, as the x values increase, the y values increase as well. All right, x is low, y is low, x is in the middle, y is in the middle, x is large, y is large. Therefore, here we have a positive association. All right, once again, there we are. Now, what is the correlation coefficient? What is the R value associated with this graph? Well, again, since it has a positive correlation, we're not going to consider any negative R values, because a negative R value tells us that we have a negative correlation. So we're only looking at the positive R values. We said that there is correlation, which means there's only one possible outcome, which means this must be 0.634. And you're going to notice the weaker the correlation, the lower or the smaller your R value will get. Smaller meaning closer to 0. All right, let's look at this next one. So the next one, do we have a relationship here? All right, definitely not linear. If I draw it linearly, then these points are going to be further away from any line that I choose to draw here. All right, so that kind of looks like it's not happening. It doesn't look like I can draw some sort of parabola or logarithm or anything like that. So I'm going to say here no relationship. It means that these scatter plots, or this scatter plot, is just scattered all over the place. Not enough to make a relationship for any type of line. All right, so next, if we have to pick one here from this box, I'm going to say weak. We have a weak relationship at most. All right, if there's anything less than weak, then I would go with that. All right, and so here I'm going to also say that because I have this weak, value that I have no correlation whatsoever. No correlation. All right, perfect. So go ahead and fit that in there. It says no correlation. Now, am I looking for an R value? Well, let's see. Looking for an R value in this particular case, there will be an R value because I chose no relationship here. There will be an R value, but the R value will be very, very, very close to 0. Now, which value is closest to 0? Well, that's going to be this one here, the R value of negative 0.02. All right, looking pretty good so far. Let's work with the next one. All right, do we have a linear relationship, a nonlinear, or a no relationship at all? Well, let's see. Take my ruler here, and it looks like I might be able to fit most of these points through a best fit line. All right, so it does look like I have a linear correlation. Nice. Next one. Is it perfect, strong, moderate, or weak? I would say it's more along the moderate line. Next, is it positive, negative, or no correlation? Well, as your x values increase, what's happening to the y values? The y values are decreasing. This means that we have a negative correlation here. So this is negative correlation. All right, nice. Now finally, what is the R value that will tell us this? Well, in here, there are two R values that are negative that are left over that we haven't chosen just yet. One of them is slightly stronger than the other. Notice the second graph is going to be a little bit more stronger than this one. So for this one, I'm going to go with negative, at the R value is negative 0.735. Now, I want you to finish off the rest of the two. See if you can finish off the rest of the two and see if our answers are going to match. All right, so take some time, put pause on the video, and see if you can do the last two on your own. And I'm also going to put pause on my video, and I'm going to fill them in. Once you unpause and once I unpause, then we'll have the answers on screen, and then you can double check to see if you got the same answers as I did. All right, so you're on the honesty scale here. Put pause on the video. All right, so here's what I have for those two. For the second to last, that was a linear correlation. It's very strong. It's a negative correlation, and the R value was at negative 0.89. The very last one is not a linear correlation. All right, there is a correlation, but it's not linear. Typically, this correlation fits more of a parabolic correlation, which means it would be modeled by some x squared value. And in this case, it would still be strong because even though it's nonlinear, it's a strong nonlinear, meaning that there is no correlation that we can see using our typical linear correlation values, which means that there will be no R value depicted here. All right. Now, remember, the R values only measure linear relationships. Since this is not a linear relationship, this is nonlinear, then the R value will not exist here. All right. Now, the value of R squared is the proportion, and that's this piece down here, is a proportion of the variation in Y that can be explained by the linear relationship between X and Y. All right. Now, we want to be able to observe the R squared value. Typically, we use technology to either extract an R value, in other words, a correlation coefficient, or the R squared value, one or the other. All right, both of them are going to tell us the very same thing, except the correlation coefficient, the R value, tells us a little bit more. All right, now, what we're going to be looking at here is that we're going to be identifying different samples that will produce different scatter plots and therefore produce different correlation coefficients. In other words, different R values. So what we want to do, or what our job is to take large enough samples to to get close to the true population linear coefficient called rho. All right, so this is your Greek letter rho. Oops, Greek letter rho. All right, there we are. So again, very, very similar to what we were doing before, right? When we were doing this hypothesis testing, we wanted to make sure that we choose large enough sample sizes. Is the sample size large enough? Right? Because again, at the end of the day, we want it to reflect the true proportion or the true population that it is that we're observing. All right. So in this particular case, again, we're going to make sure that we take a large enough sample that way we can approximate or we can get close to the true population linear correlation coefficient called rho. All right. Now, under all circumstances, we are always going to assume that there is no correlation and try to prove otherwise. Anybody ever heard that innocent until proven guilty in the justice system? Well, in the justice system, at least here in America, if you're charged with something, you go into the trial innocent. You go into it innocent until the into the prosecution can say, hey, we have enough evidence stacked against you. All right. It's at that point in time that you will then be called guilty, when there is enough evidence to say, hey, that's it, you're not innocent anymore, you are in fact convicted. All right. So again, innocent until proven guilty, or in this particular case for us, assume that there is no correlation until we prove otherwise. All right. So for me, innocent and then not innocent. All right. So the process for hypothesis testing here works the exact same way that we were to look at back when we started in chapter 8 with this hypothesis testing. We want to make sure that we have a null and an alternative hypothesis. The null hypothesis for us is what we're always going to consider, that there is no correlation between these two variables. Explanatory and response variable, no correlation. However, we're going to look at all of our data. Within all of the data, are we going to establish that there is a correlation? Well, that's what we're trying to prove. That's what we're trying to show. All right. So we're going to need to know how to pull off a test statistic. Sometimes that's going to be beneficial. The degrees of freedom here for this for this test statistic is going to be n minus 2. Be careful with that. All right. So this DF stands for degrees of freedom. Degrees of freedom is n minus 2. N is again sample size. So remember, n is your sample size. All right. Awesome. Now, to use your p-value method or the critical value method, again, we're always going to be looking at that shaded region. Remember what I call that shaded region? I always called it your friend zone, simply because if you fall in the friend zone, you get rejected. All right. So if we ever fall in that shaded region, we're going to reject our null hypotheses. All right. Remember that other device that we used? If the p is low, the null must go. So either way that we use, or either values that we use, we must always look at either the p-value or the critical value method. Now, as far as our conclusion goes, again, we're going to be looking at two specific regions. The first region in here, let me redo this here. This first region in here is going to be the region that we have no correlation. And that's this region in here. As far as the bell curve goes from the up top, this is that region right smack in the middle. All right. Now, our shaded region, the region that we are concerned with is this region right in here. In other words, that region is going to pass some random 2 standard deviation process that we typically want to look at. All right, and that standard deviation is then going to be denoted by your level of significance. What is the level of significance that we want? Do we want it to be a 0.05? Do we want it to be a 0.01, a 0.1, whatever that may be? If at any time our test statistic falls within this shaded region, then we do have a correlation. And again, depending on where it falls, if it falls on the right region, then there's a positive correlation. If it falls in the leftmost region, then there is a negative correlation. Nonetheless, as long as we fall in that shaded region, we will be looking to reject. All right, so that's going to be awesome, and that's going to be stuff that we then need to know and we then need to see. All right, so that's going to be good. Now, let's start looking at the information given to us on this first example. All right, so on this first example, we're going to be looking at this table that says the following table gives information on average saturated fat in grams consumed per day and cholesterol level in milligrams per centiliters of 10 men taken from a simple random sample. All right, so there's a lot of information being given to us here. One of the pieces of information that is being given to us is that this is taken from a simple random sample. That's going to be awesome. I'll just keep that in my back pocket. All right, now sample of 10 men. All right, so this is going to tell me that my N value is going to be 10. Awesome. Now my table lists first sample, second, third, fourth, fifth, sixth, 7, 8, 9, 10. So here are all the 10 samples, and here is the fat consumption in milligrams, and here is the observation for the cholesterol level that we're looking at in milligrams per centiliter. All right, so what I want to do at this point in time, as the question directs right down here, it says use a 0.01 significance level to determine if there is a linear correlation between saturated fat consumption and cholesterol level. Okay, so let's start looking at this. We want a null and we want an alternative hypothesis. All right, so let me go with that. What's my null and what's my alternative? So in here, the actual question says that I want to determine if there is a linear correlation. Determine if there's a linear correlation. Now, because of that linear correlation, that's going to tell me that I'm going to be looking at rho. So I have my null and I have my alternative. Null hypothesis is going to be that there is no linear correlation. Alternative will tell me that there is some type of linear correlation. All right, but what does this tell us? What type of test is this going to produce? It's going to produce a two-tailed test. All right, so I'm kind of keeping that in my back pocket. This is a two-tailed test. I have my null and my alternative. Now I can go through and I can start extracting everything else that I need. All right, so what I'm really quickly gonna do then is I'm gonna go over to the TI-84 and I am going to start inserting all of these values into two different lists. I'm gonna use list 1 and I'm also going to use list 2. All right, so all of this row here is going to be list 1, and then all of this bottom row here is going to be list 2. All right, so follow me along and we'll go ahead and we'll insert all of this into our lists. So here I am on the TI. Now what I'm going to do is I'm going to insert the list. So remember how to access the list. We're going to press second and then we're going to go to list. There we are. And I want to edit the first one here. So let me go back out. So I'm going to go ahead and hit stat. All right, so hitting stat and I want to edit the first one. So stat, then edit. There we are. And it's going to allow me to insert my list. So remember, list 1 was at 55, 68, then it was 50, then 34, then 43, and 58. Oops. There we go, then 58. There we are, it's looking good. 77, 36, 60, and 39. Awesome. So that's all of list 1. Then I'm going to hop on over to list 2. I just hit my right arrow. List 2 was 180, 215, 195, 165, 170, 204, 235, 150, 190, and finally 185. There we are. All right, so we got these on our list, list 1 and list 2, like we initially said. Now what I'm going to do is I'm going to exit this. So again, I'm just going to go to second and then quit. So second, quit, there we are. All right, awesome. Looking good so far. Now, what I'm going to do now is I'm actually going to go and run a linear regression t-test. In order to do this, we're again going to hit stat. So we go to the stat button. We make sure we get that. We're going to go over to tests. So scroll on over 2 times to get to that third column which says tests. And then we're going to scroll down until we find linear regression t-test. So notice we don't see it here on the first screen, so I'm just going to keep scrolling down until I see linear regression t-test. All right, it should be towards the bottom. All right, there it is. All right, notice we have 2 of them. One of them is a linear regression t-test. The other one is a linear regression t-interval. I want to test because I'm doing a hypothesis testing, which means I want select F here. All right, let's select that. Now it's going to ask me for my input. What are the inputs? Well, my explanatory variable was L1. My response variable was L2. So L1 and L2, there we are. Frequency, I'm going to keep the frequency just as 1. And again, this is a two-tailed test because we want rho, in other words, that correlation coefficient, to be not equal to 0. And I'm just going to go all the way down to calculate. All right, we get a lot of beneficial information here. The rest of the information that is given here, we will be able to extract at a later time. But for right now, I only want to focus on one item. All right. That one item is going to be this t-value that I'm given here. All right. Not only that t-value, but I'm also going to be looking at this p-value. So keep these 2 in your back pocket. All right. We want to keep those 2 in our back pocket. Now, what I want is I want this R value. This is that correlation coefficient that I am looking for. So again, we want this R value. All right, so now that we got the R value, let's go back and let's start working on this test statistic that we need to extract. So the R value here is 0.9079. All right, let's go ahead and write that down. All right, so really quickly, I'm just going to make a note here, and I'm going to say from calculator, correlation coefficient was 0.9079. And why do I want this correlation coefficient? Well, the reason I want this correlation coefficient is because in order for me to calculate this test statistic, I need to figure out what my R value is. All right, so here we go. Let's calculate that test statistic here. So that test statistic is going to be our correlation coefficient at 0.9079. There we are. Divided by the square root of 1 minus 0.9079 squared. That's my R squared value. All divided by n minus 2. Remember, n for us was 10, so n minus 2 That's just going to be 8. So we could write this 10 minus 2. I'm going to go back to the calculator really quick, and I'm going to insert all of this in there to make sure that we get the right values. All right, so let's go back to the TI, make sure we insert this in. Here we are. So what I'm going to do is I'm just going to clear this. I'll come back to this screen at a later time, so don't worry about it. We'll come back to it. So let's go ahead and start inserting the values that we need. So I know that I need a fraction, so I'm going to go to alpha, hit this y equals 2, get the fraction going. Numerator was at 0.9079. I'm going to go to the denominator. I need that square root, so I'm going to hit second square root. Inside of the square root, I need another fraction, so I'm going to go to the y equal to, hit that fraction, and then do 1 minus that 0.9079, square that amount, scroll down, and then do that 10 minus 2. You can naturally do 10 minus 2 here, exactly as I have it, or you can do that in your head and do the denominator just be 8, and that's perfectly fine. Alright, so once I have all of this, I'm just going to go ahead and hit enter, and voila. I get my t value, my test statistic. It's going to be 6.13 when we round off. So let's go back and let's write that down. Here we are. So according to the calculator now, we get 6.13. Awesome. So we now have that test statistic that we are looking for. Now, the test statistic, this is what we use in order to do this test using the p-value method. So in here, I'm going to say we're going to need for the p-value method. Alright, so we're going to need it for the p-value method. Now, how are we going to go about the p-value method? Well, the p-value method, we're going to need to look at these we're going to need to look at the significant level. Significance level that we are given a significance level of 0.01. So let's analyze this. All right, I need a p-value. In order to extract a p-value, I need to conduct a two-tailed test to figure out what are these probabilities here on my tails. And then I need to compare that probability with this significant level. So in order to do this, I'm going to use what is known as your TCDF. All right, so in here, let's go ahead and let's start looking at this. We're going to have some shaded region, and we're going to have some shaded region to the left and to the right. All right, so what I need to do is I need to find these shaded regions, which in here is going to be t is less than negative 6.13, and over here, this region in here is going to be the probability that t is greater than 6.13. So we have two regions. Naturally, what we want to do is 2 times whatever region we find. So we can only do one of these regions. In order to find that, we're going to do a TCDF. We're going to do TCDF, and we're only going to do this for one region, and then we just double it because of symmetry. So I want 6.13. I'm going to use this right region. I'm going to do my endpoint. Left endpoint is 6.13. My right endpoint is 1E99. Again, a really large endpoint. And I need my degrees of freedom, which is going to be 8. Alright, let's go to the calculator and let's input this in. Alright, so here I am on the calculator, and I'm going to access my TCDF. Alright, this is again a t distribution. It's going to be cumulative, which means I need a distribution. So I need to access the distribution list, which is above the VARS button. So I'm going to go second, distribution. I want my TCDF, which is number 6 here. So go down to that selection, to that number 6, press enter. We're going to do our lower bound. The lower bound that we wanted to see was at 6.13. There we are. My upper bound was at 1E99. Remember, it's not the letter E, but it's a mathematical term that we multiply by 10 to the power of and this case 99. Degrees of freedom for us, because our n was 10 samples, then degrees of freedom is 10 minus 2, in other words, n minus 2. There we are, and all I do is paste. So here we are. We get this value, but then I want to multiply it by 2. So I'm going to do 2 times the previous answer that I was looking at, which now comes out to this. Alright, so in here, I now get 2.8007 times 10 to the power of negative 4. Let's go ahead and let's write that down on paper, and then we'll work through it a little bit more. Alright, here we are. So this value gets us 2.8007 times 10 to the power of negative 4. Now, remember what 10 to the power of negative 4 is, or that e to the negative 4. That gets us 0.0002807. 1, 2, 3, 4. There we are. So it's a really small probability. This is your p-value that we're looking at. So that's the p-value. Now, we have to compare it to the alpha value. So alpha is equal to 0.01. Or 0.01. There we are. Oops. Okay, pasa. There we are. So 0.01, and this was our alpha value. So now let's compare. Which one is larger? Yeah, the alpha is going to be larger, which in this case means that if alpha is larger, that means the p is low. If the p is low, the null must go, which means we will be rejecting the null hypotheses. Alright, now that's using the p-value method. What if we don't want to use the p-value method? What if we then want to use the critical value method? Alright, so for the critical value method, there's a few more things that we need to look at, which for me is actually way easier to work with. And I'll show you why it's way easier to work with. So remember what we have, alpha is 0.01, n is equal to 10. Now check this out. What we are working with here, I'm going to center this at 0 here. And all I need to do is I need to find my critical value. What is the critical value? Well, in order to do that, we need to do one thing. We need to look up the critical value. So I'm going to say look up the critical value. Critical value. There we are. On table A5. Alright, so what does that mean? Alright, what that means is we then have to go over to the formula card that I typically give you on exams, or that you're allowed to have on exams. If you don't have the formula card, then lucky for you all, I did upload it onto Canvas, so you will have the formula card on Canvas. Or if you don't, then it's in your book. And if you don't have it in your book, I think you can do a Google search and it'll come up right away. Alright, so there's many ways that you can look this up. So let's go ahead and let's find that. Alright, here's my formula card that I put on Canvas. And notice it's just a formula card here, the same one that you always get for exams. And all I'm doing is I'm scrolling down till I see table A5. Once I see table A5, this is where I want to be. Alright, now it's where I want to be specifically because now I want to observe what is the values that I'm looking at. Well, the value that I'm looking at is n is equal to 10. Alright, so there's n is equal to 10. Now, what's my significant level? Significant level is 0.01, which then means my critical value is 7.65, or 0.765. So that's my critical value, 0.765. Now that we found it, let's go back. Alright, so from the table, we know that we get R is equal to 0.765. Now watch what I'm going to do. All I'm going to do now is I'm going to put those values right in here. This is going to be negative let's do this again, negative 0.765, and the other one is going to be 0.765. And remember, anything that falls within this region here and anything that falls within this region is going to be considered the friend zone. In other words, we're going to reject because there is enough information to support that there is a correlation. So what value then do we observe? Well, the value that we then observe, in this case, there are values. So this value here was our test statistic, critical value. The critical values were the values that we found from the table A5. So the value that I'm looking at for us is this value here, 9079. So that falls right in here. That is 0.9079. This is the test statistic that we observe. So what does that mean then? Well, that test statistic falls in that shaded region, in other words, the friend zone. So what do? We reject the null hypotheses. So whether we did this using the p-value or whether we did this using the critical value method, both methods should arrive at the exact same conclusion that we need to reject the null hypotheses. All right, so let's write a conclusion then. So the conclusion, there is sufficient sample evidence to support that there is a linear relationship between fat consumption. Oops, let's make that slightly better. There we go, fat consumption in grams and cholesterol levels in milligrams per centiliter. And we're going to say at alpha is equal to 0.01. There we are. And that's all that we need to do. And again, the conclusion should summarize, all right, what did we find? Is there or is there not a linear relationship or a linear correlation? And if there is or there isn't, then tell me that it's because of the sample evidence, and then tell me that and then tell me at what level of significance are we observing this at. All right, perfect. So that was your first example. Now let's work with the second example here. All right, so for the second example, we're going to be looking at the following table gives the total 2004 payroll on the opening day of the season, rounded to the nearest $1 million, and the percentage of games won in 2004 by each National League team. We have the Diamondbacks, Braves, Cubs, Reds, Rockies, so on and so forth. All right, we also have the payroll in millions, and we have the percentage of wins. Notice we have two different, we have two different tables, but those two different tables only show two different lists. So here, we're going to have list 1, and then this here is a continued list 1. So it's list 1. And we're going to have 3, 6, 7, 8. So we have 8 values on list 1, and then another 8 more. So a total of 16 on items onto list 1. And then down here, this is the beginning of list 2. So this here is list 2. And then down here on that second table, we just have a continuation of list 2. Continued list 2. So again, list 2 is going to have another 16 items. All right, so that's good. Let's go ahead and let's start inputting this list on the calculator. So follow me along to the TI, and then we'll go through and we'll put all of these values in there. All right, here's the TI. Now again, I want to access the list, so I'm going to go to stat. Oops, excuse me, sorry. Let's go to stat, there we are. Edit, I'm going to go there. All right, I have list 1 and list 2. I'm going to go ahead and I'm going to clear these lists. So again, I'm going to tab up to select L1, and I'm going to hit clear. When that clears it, notice it cleared list 1, but it only activates once you hit enter. So list 1 is now clear. I'm going to go over to list 2, and I'm going to clear that. So tap up to L2, press clear, and then press enter, and that should clear those lists. So let's go through list 1. All right, we had the Diamondbacks at 70 million, then we had the Braves, 90 million, then the Cubs at 91 million, there we are, then the Reds at 47 million, Rockies at 65 million, Marlins at 42 million, Astros at 75 million, Dodgers at 93 million, Brewers at 28 million, Expos at 41 million, oops, there we are, Mets at 97 million, Phillies 93, Pirates 32, Cardinals 83, Padres 55, and Giants 82. Whoops. 82. There we are. All right. So a total of 16 items on this list. Perfect. And let's go on to list 2. So list 2, the percentage of wins, 31.5 was the first number, and then you're going to keep going. So take some time, go ahead and do this. All right, so I went ahead and I entered every value on the list. Once I have all this on the list, I'm going to go ahead and I'm going to quit out of here. There we are. And what I want to do again is I want to run that linear regression t-test so that I can extract what my correlation coefficient is going to be, the R value that I'm going to be looking for. All right, so let's go through and let's figure this out. All right, so again, I'm going to want to go to stat, tests, and I'm going to hit up instead of down because I know it was one of my last ones. And so if I hit up, it automatically takes me to the bottom of the list. And here we are, linear regression t-test. Press enter on that. Again, I input my explanatory variable onto list 1, my response variable onto list 2. Let's go through. This is a two-tailed test, and I'm going to go to calculate. Awesome. Now, again, I want to scroll down and find that correlation coefficient. That R value that we're using here is going to be 0.4822. So let's go back and let's write that down. Here we are. All right, so again, I got the correlation coefficient that I got from the calculator, which was 0.4822. And that was from calculator, from the TI-84. Nice. So let's go through and let's state the null and alternative hypotheses. Null and alternative. Remember, what I'm looking at here is I'm trying to test if there is a correlation between payroll and percentages of games won. What that means for us, we need to determine if there's a correlation, which means population-wise, we're going to assume that there is no correlation. In other words, that the linear correlation is equal to 0. And we're going to try to identify within the stats given or with the information given, is there some type of correlation? All right, so I need to extract my test statistic here. So my test statistic here, I'm going to use that formula, which again is going to be that 0.4822 divided by the square root of 1 minus 0.4822 squared divided by n minus 2. So again, n was 16, so this is going to be 16 minus 2. Let's input this into the calculator and see what we get. Alright, here we are in the TI. I know I'm going to need a fraction, so I do my fraction symbol. my numerator, 0.4822. There we go, let's go downward. I need my radical. Then I need another fraction in there, so I'm going to insert my fraction. Numerator was 1 minus 0.4822 squared divided by n minus 2. n minus 2, 16 minus 2, that's going to be 14. So again, if you wanted to enter 14, that's perfect. If you wanted to enter 16 minus 2, that's perfect as well for that denominator. And all we do is hit enter. Then we get our t-value, or this test statistic, to be 2.06 when rounded. Let's go back and write that down. Here we are. So this was 2.06. Awesome. Now, you might be asking, well, hey, Mr. Castor, why do we then look at this? Well, I'm going to tell you this, that we can look at this test statistic, one, that we calculate it manually, or two, that we actually let the calculator do the work for us. All right? So I'm actually going to hold on to that piece of information that we let the calculator do it for us. All right? Because I'm going to show you a trick to all of this in just a little bit. All right? Now, remember, we need this test statistic for the p-value test. So need for, whoa, ¿qué pasa? Here we are. So need for the p-value test. All right, so why do I need it? Well, I need it because I'm doing a two-tailed test here. All right, so I need to find the probability that t is greater than this value, 2.06, and that's going to be this shaded region. All right, that's a shaded region in there, or this shaded region, which means that my p-value is going to be less than my t-value for negative 2.06. All right, but again, since we're working with two of them, two values here, two regions, we're going to do 2 times TCDF. And again, I'm just going to use the top part here. So the top value, that's 2.06, 1E99, and my degrees of freedom, which are going to be 14. So let's go back to the calculator and let's insert all this in. All right, here we are. So I'm going to do 2 times my TCDF. So in order to access your TCDF, again, you need that distribution. So we're going to do distribution here. I need that TCDF. Going down to number 6, there we are. My lower bound was at 2.06. Upper bound was the same one. Degrees of freedom, we instead had 14. There we are. So 2 times that TCDF, look at that. We get approximately 0.058. Be very, very careful. There is no e to the power of here as our answer, which means this is the exact decimal that we need. So let's go back and write that down. 0.058. Here we are. So this now gets us 0.058. And we need to compare that to our significant level. Level of significance, what was that alpha level? That was 0.05. Which means we need to compare this to 0.05, which is our alpha level. So we have the p-value and we have the alpha. Which one is larger? Well, this one's larger just by a little bit. The p is not low, the null must not go. So, in this case, do not reject. Or you could say fail to reject the null hypotheses. Now, remember I said we're going to keep all of that information in our back pocket. So, I'm going to go back to the calculator really quickly, and I'm going to show you how all of these calculations are actually done way easier. Here we are. Sorry about that last one. I switched the camera view. All right, so what I want to do now is I'm going to go through and I'm going to run the exact same thing that I did at the very beginning of this problem, which was running that linear regression t-test. All right, so linear regression t-test is what I want here. So go over here, go find linear regression t-test. Again, we're going to do the exact same thing, so I'm not going to change anything here, and I'm just going to hit enter. Now, watch this. Look at your t-value here. Is that the same test statistic that we calculated? It sure is. We did the formula way, however the calculator said, oh yeah, by the way, you don't need to do the formula way, here it is. What's that p-value that we have listed here? 0.058, or we could say round it off to 0.059. What was the p-value that we got when we did it manually? It was 0.058. It's the same one. Now, if you're using the linear regression t-test, again, you can just tell me, by the linear regression t-test, this is what I found right here. This is my test statistic, this is my p-value, and then you can go through and work with those figures. All right, so the calculator does do it for you, and it's perfectly fine. And again, remember, if you scroll down just a little bit, you get the correlation coefficient, which we'll need. So on that subject, correlation coefficient, let's go back and let's redo all of this using the critical value method, since we already completed it using the p-value method. All right, here we are. So back to the p-value, or sorry, to the critical value method. Critical value method, I use my alpha of 0.05 and I use my n value of 16. So from here, I need to find the critical value using table A5. So let's go to table A5 and let's look at that critical value. All right, once again, we're here on table A5. All right, it's looking pretty good. All right, so again, here's table A5. Now we're going to be looking at our n value. N value was 16, so here we are at an n value of 16. Alpha level in this case was 0.05, which means we now have a critical value of 0.497. This is the critical value that we need. So let's go back and let's write that down. All right, so my R value in this particular case is 0.497. All right, so again, if we're centered at 0, I now need to figure this out. So this is going to be, let's say, 0.0497. There we are, negative 0.497. And remember, anything that falls to the left of this is my quote-unquote friend zone. Anything that falls in there to the right is, again, quote-unquote the friend zone. If the test statistic falls within that region, then we reject. The value that we're looking for is from the TI, which is 0.482. That value is right below. It does not fall within that quote-unquote friend zone or that critical region, which means we fail to reject, or in this case, we do not reject. All right, it does not fall in that friend zone. So conclusion, what could be a natural conclusion that we have or that we can use to summarize here? Well, there is not sufficient sample evidence to support that the payroll of the National League teams, I'm just going to abbreviate National League as NL, teams has a linear relationship with the percentage of games won in 2004. And I'm going to say at alpha is equal to 0.05. And again, significance level stated. Now, this is all that we're doing in this particular case. So on the exam, I typically just want you to run either the p-value or the critical value method for these types of problems. And all of that is just run from the TI-84, minus the part where you have to use table A5. But again, if you're using table A5, then that's fine because you're only extracting one value from there. Everything else, you need to show me what's going on. All right? So if you just tell me, hey, from the TI, I'm extracting this, then perfect, that's great. But again, be very careful. If you're going to do that from the TI, you have to make sure that you're entering every single data correctly. All right? So, I hope you all enjoyed this lesson, and that's going to wrap it up for section 10.1. I'll see you all next time for section 10.2.